All right. So I'm going to share the screen. Let's look at 11.6. Give me a second here to copy that information down. So you're given a function xy times the quantity 1 minus 10x minus y. We want to find critical points. We want to find whether they're min, max, or saddle. So, all right. And then, of course, how you enter them, that's a whole, they're just telling you which order. Um, all right. Well, let's take a look at that. So I'm going to switch my camera here and get that light turned on. Uh, you know what? I'm going to go ahead and distribute. That way, when I take derivatives, it's a little easier. I don't want to use the product rule. So we take partial f partial x, so that's going to be y, take away 20xy, take away y squared, and partial y is going to be x, take away 10x squared, take away 2xy. And I'll pause there. Does that make sense?
Yep. Yeah.
Okay. So then what we do is we set them equal to 0. We're going to form a system here. Um, And now it's just a matter of figuring out how to solve it. This is a nonlinear system. So I think what, you know what, we can factor in the top one, we can factor out a y. And in the bottom one, we can factor out an x. And then that immediately gives us one solution, 0, 0. Of course, x and y. Okay. Because of these guys in front. You see that?
Yeah. I guess
Okay.
the because like I understand you set it to zero and then you solve for when x is zero
Uh-huh.
and y is zero. I where I kind of get caught up is pairing them together to
Yeah.
make a critical point. Like,
Well, it has to make the system true at the same time. So if X and Y are 0, that'll make everything 0 at the same time. So this is a
gotcha.
legit critical point. Now it gets a little tricky on this one. I've seen this one before, of course. We can actually take this one, these two terms here, and make a system, ignoring the leading X and Y for the moment. So I'll just copy it down here. Now this is a linear system, and what I'll do is I'll clean it up a little bit. It's going to be 20x plus y equals 1, 10x plus 2y equals 1. You know, I'll bring the ones over and make some negative, but then I just drop the negatives. And now this is a linear system, and how you solve it is completely up to you. I don't really care as long as you get it to work. Um, I'll multiply the bottom by -2, and that'll give me, let's see, it gives me negative 20x, take away 4y equals -2. That drops out the x's. I get -3y equals -1. So y is a third. All right, so that gives me something. And then when I go back to substitute, oh geez, I get fractions. I'm just going to be lazy on you guys and just want to plug in the 1/3. I'll plug it into this guy. So that's going to be 20 thirds. So 1 minus 20 thirds is, I should know that, -17 thirds. Okay. And assuming I didn't make any silly mistakes, that should be another solution. So I'll put it up here.
Wait, so you plugged in y equals 1/3 into
I actually,
20.
oh, you know what? I did that wrong. Gosh darn it. Oh, yeah, I did it. I plugged it into the X.
Okay.
So no, scratch that. I'll just plug it in here. Yep, my bad. So that's 1/3. Take away from one, you get 2/3, and then when you divide by 20, you get uh, 2/60, so 1/30. Oh, geez. Let me just double check that. If I plug the 2/3 in here, yeah, it'll work. Okay. All
Okay,
right.
so
Sorry about
you
that.
no, it's okay. I just want to clarify so I understand. So
All right.
you solved and got y equals 1/3 as one solution, and then plugged that back into the original one. If
Yeah,
you
one
plug
of the
that back into
originals.
the if you plugged it back into the other one, you would just end up getting like 0 = 0 or something, right? I mean, it wouldn't. Or no, what would you?
No, it doesn't really matter where you plug it into. It should
It'll
generate the other,
the
it
same
should generate the
result.
corresponding X value.
Okay, got it.
Now, here's the thing to keep in mind. If I plug in 1/30 and 1/3 for X and Y respectively, that'll drop out the guys in the parentheses here.
Right.
Okay. Now, interestingly enough, there are two more answers, and it has to do with what you got from back here. Because if I make X and Y 0 simultaneously, that drops everything out. But check this out. What if I make X 0, but I make Y something else? Well, that 0 would drop out the 20X here. Do you see that?
Mm-hmm.
So suddenly you can just visually look at it. That would make Y equal to 1, wouldn't it?
Yeah. Okay.
So if X is 0 and Y is 1, that actually drops out this term here. And that's a critical point. So I'm making a little list of critical points here. I've got 3 of them. And the same argument applies here. If Y is 0 and I don't force X to be 0, if I come down here and I plug a 0 in for the Y, then that makes X would be 1/10.
Okay. So you're essentially identifying roots for each value or each variable, and then plugging that back in to solve for the corresponding other variable.
Yeah. For nonlinear systems, there's really no algorithmic way to do it. You just basically locate answers and just start plugging them in, and it's a lot of algebra usually. Um, so we were able to get 0, 0 pretty quickly just by looking at these guys on the outside. That's one solution. We were able to get another solution by comparing these as a system, which we did down here, and we got this guy over here, 1/30 and 1/3. But then we come back and we say, well, what if I make X 0, but I don't make Y 0? Well, if that's something else, I can force this to be 0. Again, I just popped in the 0 for this. That drops out the 20X entirely. I just have 1 minus Y. That would make Y 1. And that's another solution. That actually makes the whole system be 0, 0, 0. So a lot of what I've seen on this particular problem in the past is that people um, they get the first two that we got here, the 0, 0, and this one here, and then they don't get the next two. That's a
Yeah, I
common
think
mistake.
that's kind of where I guess I need to brush up on solving systems. I haven't really
Well, with
touched that in
linear
a while. So.
systems, you have a lot of options. With nonlinear, because there's so many ways nonlinear systems can take shapes they can take on. There really is no just one way to do them. You basically just jump in with algebra and hope for the best.
Okay.
Yeah, it's one of those. It's like the Wild West. Um, so we've got 4 critical points now. As far as okay, so normally, let me go back to the question here. They just want the X and Y coordinates, and they want you to classify them whether they're min, max, or saddle, or cannot be determined. So you do that by doing the second derivative test, which I'll do right here. The second derivative test is d equals f sub xx times f sub yy minus f sub xy quantity squared. And f sub xx, where you come, oops, right here, and you take the derivative, that's just going to give you negative 20y. F sub yy, take the derivative with respect to y, that drops out, that's negative 2x. And then the mixed partial, so if I do f sub xy, I get 1 minus 20x minus 2y. Now check this out. If I do f sub yx, I get 1 minus 20x minus 2y. I get the same thing. Okay. That's a good check. That should always happen. And then what you do is you just plug in the points. So I'll make a little table. I want to try to keep everything fit there. So I'll just make a tiny little table here. So 0, 0, I just pop them in. I get 0, 0, and then these just drop out entirely. This drops out. You get 1 squared, you get -1. So that's your D value. That means D is negative. That's a saddle. Did y'all see that?
Yeah,
Let's
makes
do
sense.
let's do a couple more here. 0, 1. So if you pop in a 0 for X and a 1, well, that drops these guys out again. Looks like we're going to get another saddle here because, well, hold on. Let's actually do it. So 0 and 1. So 0, that just drops this out. Here, that drops out this guy. But this is going to be, it's still going to be negative. We're going to get 1 minus 2, -1. But that's square. Okay, so we're going to get a -1 again. So we get another saddle. Let's try it for 1/10 and 0. I think we're going to get the same thing because it's going to drop out these guys. And at 1/10, oh, this is interesting. No, this works.
Wait, won't we get, I'm sorry, won't we get +1? Because you'd have 1 minus 2 times 1 is -1, and then that's, oh, but then it's the opposite of that
Yeah,
quantity.
you actually have a triple negative.
Yeah,
Believe it
okay.
or
Thank
yeah.
you.
Yeah, and then you know what? I think we're going to get a -1 again. Looks like we're going to drop out, or we're going to get a negative value because that'll drop out this guy. That'll make that a 2, and 1 minus 2 is -1 squared 1. Okay, yeah, it's interesting. We got 3 saddles. So hopefully we get something interesting out of this. And then the last point was this 1/30th and 1/3. And we pop these in 1/3 for Y. I'm going to show you a little trick here. I don't actually evaluate them all the way. A 1/3 for Y would make this -20 thirds. A 1/30th for X would make this -1/15. And then 1 minus, so X is 1/30th, that's -2 thirds. And then 2 -2 thirds again. Making sure I do that right. Let's say I get 1 minus 2 thirds is -1/3, minus 2 thirds is -1, squared is 1, that becomes -1. So I'm going to write it, well, I'm trying to do this in my head. This is -20, and well, the negatives will cancel. We get 20 over 35, no, 45, 20 over 45, take away 1. Do we get another saddle here? Um, Let me double check my math. Yeah, looks like we do. Interesting. I can't imagine we get all saddles because this whole thing will be negative. So that'll be another saddle. Hmm. Looks right. I don't think I've made any mistakes. I'm just kind of skeptical. Why would you get 4 saddles?
Would that be like the oh God, what are they called? Like not hyperbolic, but the parabolic. No, is it hyperbolic? The one that kind of just looks like a bunch of saddles in like four directions.
Well, you know, I don't know. I don't think so. I wonder if I made a mistake. I'm going to go run through my math again here. 0, 0. This just drops these guys out entirely, unless Um, I wonder. Yeah, I'm kind of doubting myself, but I don't see any mistakes. I keep on getting negative D values each time, and that'll be a saddle. The first three, I'm not surprised, but the last one, if I put a 1/30th here, that's -2, or so -1/15. Put a 1/3 there, that's -20/3. 20/45, 15, 30, 45. That's correct. And then this is going to be 1 take away 2/3, which is, oh, you know what? Okay, that's my mistake. Yeah, right here. I think I made an arithmetic mistake. 1 minus, so 3/3. Yeah, gosh darn fractions. Um, so that should be -1/3. So this will be 1/9 after I square it. Yeah. All right. All right. I'm feeling a little better about that. So 20/45 minus a ninth is a positive quantity. Okay. And then when I come back here and I look at these two guys, these are both negative. That tells us we have a max. These are both concave down. The D value itself is really not that relevant. It's just we're only looking at the sign of the overall expression, whether it's positive or negative. If it's negative overall, it's a saddle. If it's positive, then we have to look at the first two terms. And usually well, actually all the time, they'll be the same sign if the overall sign is positive. You know what? If doing a problem like this, sometimes I'm going to graph it. I'm going to see what the thing looks like. Are you guys all right with that?
Absolutely.
Yeah, let's take a look. I'm going to go to Desmos. I'm going to go to the 3D option. I'll share here. Give me a second. Now, of course, sometimes these graphs look crazy, so I will just hope for the best. The original function was, well, I distributed. It was xy, take away 10x squared y, and then take away xy squared. Oh, geez. Yeah. Let's see if we can make sense of this. The 0, 0 right there, that's the origin. That was one critical point. Can you guys see my cursor when I move it?
Yes, sir.
Okay. That looks like a saddle. Yeah, sure enough. It looks like it's like it's a weird saddle. Okay. Um, 0, 1, that would be 0, 1 on the y. I'd put us right here. And that is a very gentle saddle. Yeah, that's a saddle too. At 1/10 and 0, oh my gosh, that puts us barely like right there. That I'm using the kind of like the shading here, like the darker red is above the XY plane and the pink is like below. And you can see, like below, below, above, above. So when you see that kind of like four square effect, so that looks like a saddle right there. Oh my gosh. And then the other point is 1/30th and 1/3. Oh my, I don't even know if we can see that. See if I can zoom in. Um, that would be 1/30th and 1/3. It's going to put us right about here. Oh, I don't know if you can see that. Do you see that little tiny ridge right here? Maybe I'm seeing things, but the math says that that's a local high point, like a little tiny. See if I can get it. Let me see if I can zoom in. Yeah, can you
Yeah,
see
you can
that?
see it at the top of it. Yeah.
Just barely. Oh my Lord. What a sneaky function, right? Yeah, it seems like the math and everything adds up. That was a good problem. Um, let me make this bigger. Can you guys, okay, so we did a lot of math there. Is there any, I can take time here and go over any part if you want some further explanation.
I think that made good sense. I think I understood that, like, I guess the concept, like the steps of like, okay, you do this and this. Where I got caught up, I think, was mostly just solving the system, and I got caught up because I would find the, I guess, components of the critical points and then be like, well, which one goes with which one? But yeah, that makes a little more sense. So I think it'll be good.
Okay, yeah. Just to reiterate, um, nonlinear systems like you see up top here are, there's no algorithmic way to do them. Have you guys taken your linear algebra yet
No.
before
Yes.
you? So you're taught a whole bunch of ways to solve systems, but those are all linear systems. Nonlinear, there's just really no way. And a lot of them are actually quite difficult to do because of the algebra. This one works out, still takes a bit of effort. And a lot of it is just, I don't know how to put it. You just kind of beat it with a stick until it works. We found a couple of solutions fairly quickly, and then you kind of have to be clever with the other solutions. Um, and then we checked them each by using this second derivative test, and then just checking the sign of D, and then noting what we had here. So we had three saddles and a local max. All right. That was number 6. Did you want 7 as well? How different was that one?
It's similar other than the fact that it has bounds for which it wants to know where the minimum and maximum are. And that was kind of another one that I think probably for about the same reason, but
Yeah, give me a second here. I lost my place. 11, 7, number
7.
7 this time. Yeah, I backed out too far. Um, yeah, let's take a look at that one, if you don't mind. Okay, so to kind of compare between the two, in this particular example we just did, this is an example of unconstrained optimization because other than, well, in this case, there were no constraints on X or Y. Other than any domain constraints, you're free to roam all over whatever the domain may be. In the next example, the domain is actually restricted slightly. So let me share the screen. And I'll copy this down. We have a function. This is 11, 7, number 7. Function is xy take away 7y, take away 49x plus 343. And your region is above y equals x squared. I'll call it big R. And below y equals 50. So if I'm going to graph that right now, actually, it's just a parabola that opens up. Then up here, we have a line at 50. Okay, so I'm going to stop the share. We want to find absolute min and max. Okay, so we're constrained to this region and the boundary. Okay, so generally when you have constrained optimization, you check 3 things. Check any corners or extreme points. Check the boundary itself, and then check the interior. Okay. So why don't we just kind of run through them? As far as the corners go, that's not that hard to do. We have 0, 0. We have, it's going to be square root 50 and 50. This is going to be negative square root 50 and 50. And I'm not going to bother messing around with those for now. What we're going to do is we're just going to create a massive list of critical points. These are 3 automatic critical points. When we check the boundary, so we've done number 1. When we check the boundary, we have to check them one at a time. At y equals x squared, you just simply substitute x squared into the function. And what happens is it just becomes a traditional f of x function. Okay. Now this is a cubic. It looks like it'll work. I think if I take the derivative, I get 3x squared, take away 14x, take away 49. And then that doesn't look very friendly. So I want to set it to 0. And so I'm going to use the quadratic formula. So that's going to be negative of negative 14. And then we have negative 14 squared. Take away 4 times 3 times negative 49. And that's going to be all over 2 times 3, which is 6. I'm just going to do a calculator. So give me a second here. We got 4. I'm doing the inside, so it's 14 plus 4 times 3 plus times 49. Oops. So I get 14 plus or minus rad 784 all over 6. I'm going to get 2 answers out of this. Let's see what we get. So when I do 14 plus that, well, I get 7. Interesting. And when I do the alternative, I get negative 7/3. Interesting. So I got some nice answers. I was expecting some decimal answers. So I just have to make sure that it's in the on the region. So this rad 50 is slightly below 7. Oh, you know what? This one's not. So wait, this one's actually outside the region. However, negative 7/3 is going to it's going to place us right about there. Now that's just the x value. But if I can easily plug it into the boundary, that'll be 49 ninths.
Wait, I'm sorry. Is
Yeah.
the square
Right.
root,
What's that?
isn't 7 inside the bounds, or am I not understanding the bounds correctly?
Yeah, I think you're correct. Going because
Oh
square
yeah,
root
you're
50
right.
is going to be higher than 7.
Yeah, I was my bad. You're right.
Okay.
Because it should be. I was thinking, yeah, 49. You're right.
Yeah.
That's the easy one. So we're just below that point. Yeah, all right. So I can't unex it, so I'll just redraw it. All right. And then you got to do it for the other boundary, which is y equals 50. In this case, this should be not part at all. This will be 50x take away. Well, that's 50x take away 49x is x, and then 50, that's 350. Negative 350 plus 343 is negative 7. But when you take the derivative of that, you just get 1, and that doesn't help you any. You don't have any critical points. You'll just end up getting the boundary, the endpoints again. So that gives you nowhere. And then, if you haven't had enough fun, you have to do the interior now. We'll do that over here. That's where you do the partials. F sub x is y take away 49. Okay, that's not too bad. And f sub y is going to be x take away 7. All right, that's not too bad. So that appears to be that we get 7 and 49 again. And we've actually already got that. That's this point that we already got. All right, now I'll pause. Any questions on what I did? All right. I'm just looking at what I wrote down. It seems like it's working pretty good. when you have what you have here is a closed and bounded region. It's called a compact space. It just means closed and bounded. And what that means is that as long as your function is continuous, which this is, over the region, you're guaranteed an absolute min and an absolute max. At this stage, it's actually rather easy. All you do is just simply plug the points in to the original function and look for the highest and look for the lowest. So just plug in each critical point into the function itself and look for the highest and lowest. So you have 6 points to evaluate at. One of them is going to be the winner. One of them is going to be the winner the other way. So for example, 0, 0 plugs in, you get 343. Okay. Sometimes what I'll do is I'll just put a little 343 kind of right there.
Sorry, you said 6 points. So we've got the
I'm sorry,
negative root 50 by 50, negative 50, 50, 0 and 0, and then we've got 749 and negative 7/3 and 49 over 9.
Yeah.
What's the sixth point?
Yeah, you're right. No, it's 5. 1, 2,
Okay.
3, 4, 5. So you just basically just run through each calculation. This would be a calculator job. I'll do this one, 749. So it'd be 7 times 49. As usual, I can't do it. 7 times 49. Take away 7 times 49, which is 0. Take away 49 times 7 plus 343. Interesting. This one just gives you 0. Okay. And you just run through each calculation and then just decide which one's the biggest and which one's the smallest. Does that make sense?
Yeah, that method for checking the boundary definitely. I guess I don't know how. Maybe it was just the infinity stuff was giving me a run for my money, but yeah, the boundary checking was what was hanging me up last time, and that makes it much clearer. So
You know, I'm
that's
gonna
pretty
tr
good.
I'm gonna try something on Desmos. Give me a second here. I'm gonna share the screen. I don't know if this is gonna work because I can easily type in a function. I'll just call it z. So it's xy, take away 7y, take away 49x plus 343. The problem there is that my z is way the heck up there. So um, maybe I can mess with the. I'll tell you, I'm going to take off the 343 for just the moment. No, that's not going to do me. What I was going to do is I was going to try to graph the region itself because sometimes you can do that. Sometimes you can say like y equals 50, and then it asks, oops, you can extend that to 3D. The problem is I have to scroll way out. Now we're starting to get some shapes here.
Hmm. So is y equals 50 an asymptote for this, or
It appears, yeah,
no? It looks like
well,
the
not quite. No, it appears we have a saddle there.
okay.
I'm not really sure how do you classify that. They're hugging pretty close. I don't think that's quite asymptotic. Now, let me do the other thing. I'm going to try the other thing. I'm going to try it where I go y equals x squared and then extend to 3D.
So yeah, we're really only looking at that. Okay.
Well, I've got the bounds in there. So the purple and the green are the bounds. The problem is, and I'm kind of goofing around with this in real time. I'd like to get, maybe I can get Z because I want to get it up there. I want to get, let's make it 350. And then let's make the x bounds not very big, maybe -8 to 8. Oops. And then let's make the y bounds, that'll be 0. Maybe I'll just make it like -5 just to have some space. And the top y bounds was like 50, so I'll make it like 60. It's a little better. And then the z-axis, I don't need well, I don't know actually. I'll try -50. All right, so let's see if this works. The blue is your surface. So you know what? I'm going to make the top bound a bit bigger. I'm going to make it to 400. Maybe actually make it 450. Okay, now we're getting something.
Mm.
Oh, wow. All right. Let's see what we got here, people. The green and the purple are your bounds. We're looking at the surface, the blue surface that's within those bounds. And you can see, for example, if I were to orient it so that you're looking straight down, there's your y equals 50, the green, and there's your y equals x squared, the purple. And you can see that it looks like we're gonna get a high point here. That would be my -7/3 and 49/9. I'll bet you that's your highest point.
Your lowest point is that 0 that we calculated at 7 and 49.
Yeah, it's right here. And it looks like at these corners you actually creep up a little bit, don't you? Or do you actually go down a little bit?
I
I
think at
don't
the
know.
corners you actually go below the XY
So you
plane
maybe
and
get a
Right.
little
get a
bit of
little
a negative
negative.
value. Let's see if we can see it. So you can turn it around. It's kind of hard to but you're trying to find where the green and the purple intersect. And you can see it where my cursor is down here. The blue is going to be slightly below.
Yeah.
Ooh, that's pretty subtle. And then I think it's the same thing happens over here. Not quite, actually. It looks like they're a little bit above here. Actually, this worked out pretty good. I was kind of surprised. I didn't think I was going to get this to work, but this 3D graphing is pretty robust. I'm pretty pleased with it. You see how I kind of figured it out by looking, kind of, sort of?
Yeah. Could you even just plot the points that you kind of come to
Let's
the
try.
conclusion
I don't
of and then
know.
just see
Let's,
if
how
they're,
about 00343? Did that do me anything?
uh,
Let's try another point.
oh yeah, it's right there. It's just a gray dot,
Yep.
right? Yeah.
Yeah, let's try the -7/3. Oops, the 49/9. Now, I never actually figured that out. Um, I'll do it real quick. Just give me a moment. Comes out to be 406.518.
Hmm.
There it is. Oh, that's so sweet. Do you see it's kind of there on the little high point there?
Mhm.
There's your points. There's your 0, 0, and there's your other point. Pretty nifty, right? I like that.
It's
I'll let you
very
have
good.
this on the test.
Check.
I don't know
Perfect.
if you want to mess with it, but I'll let you have it. All right, that was a fun one. All right. Any questions on this one since I got the graph up? Anything else you want to look at while I've got the graph going? Oh, I like that one. I'm going to stop the share. How about the math itself? All right. All right. Well, that was good. Those two problems took up quite a bit of time, but that was good stuff. got about 15 minutes. Anybody else want to ask a question?
Yeah, hi. I joined a little late, so sorry
Sure.
if I missed this, but did you guys talk about 11.7 problem 8 yet? And it's very similar to this, except the boundary is a circle. And I
We have
understand.
not. Give me a second here. I'll show the screen. Hey guys, just to warn you, it's thunderstorming where I am, so hopefully I don't get my power knocked out. If I do, if suddenly I just drop off, I'm sorry. Um, so here is 11.7 number 8. And the function is 2x cubed plus y to the fourth. And you're graphing around the circle x squared plus y squared less than or equal to 9. So that's inside a circle of radius 3. So it's kind of the same thing like we did last time. If I I'll draw the region. These extreme points automatically become critical values. So, you check extreme points. We don't have any corners, but we have extreme points. So we have these three guys already. I'll just label them properly.
And I mean,
Oops.
given that the circle, like the derivative of the boundary of the circle is constant, why are the 3003, etc., extreme points? Why are they distinct from any other point on the boundary of the circle?
I don't know yet. Let's just run through it. I don't think it's going to be constant. I think that's my answer. But let's run through it. So the interior, this will go quick. The interior is going to be 6x squared. F sub x, f sub y is going to be 4y cubed. When you set them to 0, you just get the 0, 0. So 0, 0 is a critical point. And that's going to be it. So the interior is taken care of. These extreme points are taken care of. And the other thing we do is then we handle the boundary. And what I'll do is I'll solve for y, and I get plus or minus. Actually, let me think about this. No, I won't do it that way. I'll just solve for y squared. I get 9 minus x squared. Because then what I'm going to do is I'm going to plug it into the over here. So the boundary is where I plugged in y squared. For y squared, I plugged in 9 minus x squared. But this is y to the fourth, which is y squared squared. So I actually have a function just in x, 2x cubed plus 9 minus x squared quantity squared. Does that make sense?
Yeah, so I can get the function. It's x to the
Okay.
fourth plus
Let's do the
2x
derivative.
minus 18x squared plus 81.
I'm just curious what we get. This is going to be an interesting one. So I get 2 9 minus x squared quantity to the first, and then minus 2x chain rule. Let's see if this cleans up. That's going to be negative 4x 9 minus x squared 6x squared, take away 36x, take plus 4x cubed. Interesting. So we end up getting 4x cubed plus 6x squared, take away 36x. So we don't have a constant level curve on the boundary. The boundary itself is going to be wiggling up and down relative to the xy plane according to this function. So what I'll do is I'll set it to 0. Now I can factor out, I can factor out a 2x. So I have 2x squared plus 3x take away 18. So one of my answers is when x is 0. Now when x is 0, I go back up to here, and that gives me y is plus or minus 3. So that actually gives me these two guys again. Okay. The other answers are going to be from what I get right here. And again, I'll just use the quadratic formula. So I get 3 squared, I get 9. Take away 4 times 2, so negative 18 all over 4. Real quick on my calculator. It's really storming where I'm at, so hopefully it stays power on. So I get -3 plus or minus radical. Oops, I missed up. Hold on. Missed it up. 153. So I get two answers. Let's see what I
Okay,
get.
so that's good. I got there too.
Okay.
And
This, go ahead.
one of them is outside the domain.
Yeah, that's something we may end up having to
So you want
get
-3
2.34.
plus the radical.
Actually, no, that looks like it's going to work. Oh, let me try it again. Oh, okay, I see what happens here. Yeah, all right. One of them is outside the domain, one of them is inside the domain. So you'll notice that your x's are bounded by -3 and 3. One of our x's here is -3.84. That can be kicked out. However, the 2.34 is good enough. And now I am rounding here kind of harshly, so bear with me. If I take that 2.34, remember I have to go back to the original function up here, the y equals 9 minus y squared equals 9 minus x squared. So I have to plug that in. So 9 minus 2.34 squared, and then square root that. That actually gives me two other answers. I get 2.34 and 1.88. And then I get 2.34 and negative 1.88. And that's going to put me about here and here. Sorry for my sloppiness there.
Wait, you took that x equals 2.34 and you plugged it back into which formula?
Well, the original substitution for the boundary was to set y squared equals 9 minus x squared. And I did that there. That became what you see here. So everything is in terms of x now, for now. But remember, you still have a y to worry about. So once you get your x figured out, then you go back up to the y value up here. That's how you find your y. So I plugged in the 2.34, so 9 minus that squared. And then remember that's all under the radical, so because I have to square root both sides, and I get two answers, plus and minus 1.88. And I warn you, I did round pretty quick. I would actually have taken it out a couple extra places if I was going slower.
Yeah, I got it now. For some reason, I think I made a calculator mistake and I ended up plugging in a wrong answer.
Yeah, no, that's totally understandable. These are there's a lot of opportunities to make silly little mistakes, as you have witnessed. I've done a couple already. Um, so it looks like we've got 7 uh, critical points. Then your job is just simply to plug them in, each one of these guys, into the original function now and figure out which one's the highest and which one's the lowest.
Yeah, I can take it from there. Awesome.
Okay. Yeah. All right. That was a good one. And I won't do that, but if you want to goof around on Desmos, I'd be curious how well it shows it. It seemed to work for the one I did, so I would imagine it works for this one too. Well, you know what? It is a couple minutes to 7, and so we had three really good min-max questions. I'm gonna go ahead and power down here before nature makes me power down. Um, and I'll get this on YouTube hopefully soon. So I appreciate you guys showing up and enjoy tomorrow and just I'm going to be circulating grades probably again because I wanted to do them once a week. I was going to wait until Monday to be honest. All right. So again, thank you everybody. 5, 4, 3, 2, 1. Goodbye.